Okay, so previous lecture we discussed something on binding energy of a nucleus. Binding energy, as I told you, is the difference between total rest mass energy of all the Z protons and all the Z neutrons in a nucleus when they are separated from each other, and the total mass energy of the nucleus made from those same protons and neutrons. When it is a nucleus, the total mass energy is low. When these are separate protons and neutrons, the total mass energy is somewhat larger, and that difference we call binding energy. And for that binding energy, we were trying to understand how it depends and so on. So, what we had seen is that binding energy is roughly proportional to the total mass number. I had shown you a slide on which binding energy per nucleon was on the y axis side, and the total mass number, total number of nucleons, that was on the x axis side, and barring some light, very light nuclei, most of these nuclei gave you something like 8 MeV of binding energy per nucleon, with a slight downward trend as capital A increases. Now, if I think that nuclear interaction takes place between all the pairs of nucleons in the nucleus, we should have something like capital A into capital A minus 1 by 2 pairs, and one can expect that binding energy will be somewhat proportional to A square, will go like A square, but it does not. Binding energy goes as capital A, not as capital A square. And then we discussed that the message of this experimental finding is that not all pairs of nucleons in a nucleus is able to effectively interact through nuclear interactions. So, what does that mean? That means that nuclear forces are short ranged. If you have a nucleus, of some 6-7 femtometers of diameter, and you have a nucleon here and you have a nucleon here, and the separation is say 5 femtometers, 6 femtometers, and if this pair is not contributing significantly to the binding energy, that means the nuclear force between these two is extremely small. So, the nuclear forces are effective only if the separation is much smaller. So, maybe each nucleon interacts with only few nucleons in its own surrounding and nothing outside. If I consider this nucleon, then possibly whatever nucleon are here, only with those few nucleons it is effectively communicating through in nuclear interactions, and all outside nucleons, these do not form nuclear interaction pairs. So, if you say that each nucleon interacts with small n nucleons in its own surrounding, immediate surrounding, then how many pairs will be there which interact through this? That number will be, if each nucleon, use unitary method, each nucleon interacts with small n nucleons. So, there are total capital A nucleons. So, you will have A into n pairs, but then each pair is counted twice. So, this is divided by 2 also. If each nucleon interacts with small n nucleons around, and one by one, either this first nucleon is interacting with these small n, and second nucleon is interacting with these small n, and so on, and I go from first to the last capital A, all capital A nucleons. It is capital A into n, but then remember each pair is being counted twice. Once when I was considering this nucleon as the seed nucleon, and second time when I am considering this nucleon. So, but anyway, that does not matter. So, it is proportional to capital A, and this will give you that binding energy is roughly proportional to capital A, which is observed. So, this observation tells us that nuclear forces are short ranged, maybe some 1-2 femtometers, 2.5 femtometers, and after that sharply the magnitude decreases. Okay. So, as first approximation, we will write that binding energy is some constant times capital A. That constant we write as A and then subscript V. What is this V for? This V is for volume. Volume of the nucleus, the entire nucleus. So, in this term itself is called volume term. If you have a larger volume, you have larger number of nucleons, capital A is large, and proportionately this term goes up. So, that is volume term. So, here if I say that it is proportional to A, what I am doing? For each nucleon I am saying that it is interacting with these small n nucleons. Of course, I have taken the possibility of counting it twice and all those things, but then this is some kind of an overestimate. Why? If you have a nucleon here and if you draw a surrounding volume so that it interacts with all the nucleons here and there are small n nucleons, and that is how you count and go for from first to the last all nucleons, capital A nucleons, and say that there are capital A into n by 2 pairs. The problem is for the nucleons which are at the surface, near the surface, these nucleons, a nucleon which is sitting here, this also will interact with nucleons surrounding itself, but then of that radius if you draw a sphere, spherical volume, and say that it will interact with all the nucleons in this volume. So, there are no nucleons here, it only finds nucleons here. So, it does not have n pairs, it cannot form n pairs, because it is sitting at the surface. On one side there are no nucleons. And so, if I have used this unitary method, I have overestimated the surface nucleons, the nucleons near the surface, they do not have n nucleons to interact with, that number is smaller there, and therefore, we have to subtract something from this binding energy expression A V into capital A. And what I have to subtract, that will be proportional to the number of nucleons that are on the surface. On the surface means once again there is no sharp boundary of the nucleus, but still close to the surface where this density goes very low. Proportional to the surface area means proportional to r square, capital R square. Surface area is 4 pi r square for a sphere, and proportional to r square means proportional to capital A to the power 2 by 3, because r, you remember, the radius goes as r naught A to the power 1 by 3. So, r square will be r naught square, and then this into 2, that is 2 by 3. So, something proportional to capital A to the power 2 by 3, that should be subtracted from this volume term because of the surface nucleon. So, we write the second term, and that second term is minus A s capital A to the power 2 by 3. A s, S for surface. This is a constant, AS is a constant, and it is referring to the surface contribution, or rather the overestimate that I had done earlier. I am compensating for this. So, this is known as surface term. So, you have a volume term and you have a surface term. So, this is on nuclear interactions, but then in the nucleus you have protons, and these protons interact through Coulomb forces also, and that will also contribute to binding energy. Whenever there is an interaction, there is a corresponding binding energy. Here it is not attraction. Proton through Coulombic forces will be a repulsion, and repulsion means a loss of binding energy, increase in total mass energy, and the binding energy is reduced. So, there is a further reduction in binding energy because of this Coulomb interaction. And how it should depend on the proton number? It will depend on the proton number, because it is all proton interactions through Coulomb, right. Nuclear interaction takes place between proton-proton, proton-neutron, neutron-neutron, all nucleons, but the Coulomb force operates only between the charges, electric charges. So, number of protons. So, if in the nucleus, if you have Z protons, how many pairs can be formed from these Z protons? That will be Z into Z minus 1 by 2 pairs. Will all pairs contribute towards this Coulomb part of the binding energy? Yes, it will, because Coulomb force is not a short range force. Coulomb force is 1 by r square type. It gradually decreases as r increases. The force is like 1 by r square. The potential energy of a pair, charged pair, goes as 1 by r. So, all the pairs will contribute, and so it should be proportional to Z minus 1 by 2. But then the energy, the potential energy of any charge distribution will be something like 1 by radius. If you have two charges q1, q2, what is the potential energy? q1, q2 by 4 pi epsilon naught r. R is the separation. If you have spherical volume, uniformly charged spherical volume, what is the potential energy? Once again it is some capital Q square 3 by 5, some constant there, and then 1 by r, 4 pi epsilon naught and all that, and after that 1 by r. So, the Coulombic potential energy or electrostatic potential energy will go as 1 by the separation between the charges, average separation between the charges, something of that sort. So, it should be proportional to this Z minus 1, and then it should also be proportional to 1 by radius of the nucleus, and radius once again is r naught a to the power 1 by 3. So, proportional to 1 by radius, that means proportional to 1 by capital A to the power 1 by 3. Okay. And this is to be subtracted from the binding energy, because it is repulsion. It is not giving you binding, it is repulsion. It is not binding, it is not trying to keep the nucleus bound. So, from binding energy we have to subtract this contribution, and then you get third term in this formula, and we write it as minus AC, again a constant, Z minus 1 divided by capital A to the power 1 by 3. This is for 1 by radius, Coulomb potential energy, and z minus 1 is for the number of pairs divided by 2 etc. is here in this constant AC. So, this third term is known as Coulomb term in that binding energy formula. Okay. So, these three terms, they denote the contribution from the volume, nuclear volume. This denotes contribution from the surface nucleons, and this denotes contribution from the proton pairs. So, up to here we can go with what we can call classical description. All the language I am using, the volume, the surface, the pairs, interaction energy, this is classical physics language, and this we can do from here. Taking these three terms alone and properly choosing the AV, AS and AC, that general shape of binding energy per nucleon, that curve can be reproduced. But then there are two important quantum mechanical corrections or terms which we have to add. One is what we call asymmetry term. If you remember that inverse Z diagram, if I have Z and N, stable nuclei and nuclei close to them are almost, at least for lighter nuclei, they are almost on this line, N equal to Z, and after that there is some deviation. Okay. So, why the deviation is there? In heavier nuclei you have more neutrons than protons. For lighter nuclei you have almost equal numbers of protons and neutrons. This is because nuclear force by itself prefers Z equal to N. Okay. So, in this region where the Coulomb force is not that effective, nuclear force is effective, nucleus is small, and at a smaller range nuclear forces are stronger, much stronger than Coulomb forces. So, here Z equal to N is enforced, but if the nucleus becomes big, so that the nucleon separation sometimes at the say diametrically opposite points, this separation is somewhat larger, then Coulomb force also starts showing its role more effectively. And then to compensate for that repulsion between those protons, you have to bring in more neutrons. That is why N becomes greater than Z. So, for the nuclear force itself, Z is equal to N, that is preferred composition. Why is that? Because nuclear force is charge independent. Nuclear force does not distinguish as such between protons and neutrons. Nuclear force between two neutrons at some separation is exactly the same as the nuclear force between two neutrons at the same separation, and other same angular momentum, other things. So, proton and neutron, they are equivalent as far as the nuclear force goes, but then why Z equal to N? How can nuclear force distinguish between them? So, you have to use certain quantum mechanics there also. So, that description which we will be doing in more detail later is that each nucleon finds itself in some kind of an average potential. So, if you have a nucleus containing capital A nucleons, then each nucleon you can think of that it is moving in the potential created by that capital A minus 1 nucleons, and then you have a potential, and then you have energy levels, you have quantum states, and this nucleon can occupy one of those quantum states. To get the minimum energy, ground state energy, these levels will be filled up from below, lowest energy to highest energy. So, we will talk it in more detail when we do this shell model, but roughly let us say you have these energy levels. So, energy going this side and this side nothing, just energy levels, one dimensional diagram. Now, if you have protons and neutrons, suppose you have A nucleons which is Z plus N, again assuming that this proton
spin, that is intrinsic spin, that can be plus half or minus half. The protons and neutrons are both fermions, they are s equal to half particles like electrons. So, ms can be plus half, ms can be minus half. So, assuming that energy is independent of that, at each level you can put a proton with spin plus half, a proton with spin minus half, neutron with spin plus half, neutron with spin minus half, but not more than that. In one particular level you can put 2 protons and 2 neutrons, one with a spin plus half, one with a spin minus half, because Pauli exclusion principle will be there. They are fermions, they are spin half particles. No 2 fermions should have the same quantum numbers. Okay. So, that ms can be different here and here, so that putting these 2 protons here in one state does not violate Pauli exclusion principle, right. Similarly, putting 2 neutrons here, that does not violate Pauli exclusion principle, because you can have one ms plus half, ms minus half. But if you want to put a third proton here or a third neutron here, then the Pauli exclusion principle is violated. So, that should now go on the next level, right. So, this way it can be filled up. So, if this A nucleon that I have equally divided, Z is equal to N and that is equal to A by 2, then you can just go on this scheme. If it is even nucleus, if Z is even and N is even, then you can just go on filling it in this style, this way. Okay. But suppose Z and N are not equal. Suppose you have a nucleus in which N is equal to A by 2 plus nu and Z is equal to A by 2 minus nu. It is a realistic situation for all these nuclei here, and many of the light nuclei also you have more than one isotopes. So, you can have this N greater than Z, very common situation. So, suppose it is A by 2 plus nu here and A by 2 minus nu here. So, now how these levels will be filled up? If you try to fill it again, let me draw it again somewhere here. Suppose these are the levels, the same levels I am trying to draw for protons and neutrons. Just I have separated so that I have some space to work. So, this A by 2 minus nu protons and A by 2 minus neutrons, that you can fill up just like this, right, equal number of protons and equal number of neutrons you can fill up. So, suppose here up to here you have already filled up A by 2 minus nu protons and same number of neutrons. How many neutrons are left? You have put all these protons and these many protons, same number of neutrons, but the number of neutrons you have is A by 2 plus nu. You have already accommodated A by 2 minus nu. So, how many left? 2 nu, right. This is the total number of neutrons, and this I have already accommodated up to here. So, what is left? The total number minus the number I have filled up. 2 new neutrons are still there to put. Where do I put them? I will have to put them here, only 2 of them. I cannot put all of them here. I cannot is the same energy level, remember, same, it's the same quantum state. So, next set of neutrons will go here, then go here and then go here and so on. You cannot put a third neutron here, you cannot put a third neutron here, you cannot put a third neutron here. Okay. So, what is the energy in this case, in the first case where this A nucleons are divided equally, and what is the energy here where they are asymmetric, number of neutrons is more than number of protons. Let us calculate that difference. So, first this case, So, suppose somewhere here this is the level where I have accommodated those A by, here I have accommodated these protons, these neutrons. So, this is same. After that, if there are two new nucleons left here equally divided and they are only neutrons. So, here you will go up to how many levels? How many nucleons are left? Still two new nucleons are left, but then you have new protons and new neutrons, and in each you can put two of them. Okay? So, nu by 2 levels you are going up. So, what is the energy? Suppose this difference is delta. So, let us calculate the extra energy. Up to here it is common, here and here it is common. After that, so this will be, for this one it will be, there are 4 particles at energy delta, right. Then there are 4 particles at energy how much? 2 delta. Okay. Then there are 4 particles at energy 3 delta. How many terms will be there? How many terms will be there? And nu by 2 terms. You have new protons and new neutrons. You are putting 2 in one level. So, how many levels you are going? Nu by 2. So, there are nu by 2 terms. This is, let us call it energy E1. So, that is equal to, what is to be taken common? 4 delta, 1 plus 2 plus 3 up to nu by 2 terms. This is 4 delta into nu by 2, nu by 2 plus 1 and then divided by 2. So, this 2, this 2, this 4 can be cancelled and you have delta times nu square by 2 and plus nu. Okay. Now, look at this situation. In this situation, after this these levels are filled up, you have again 2 new particles, but all are neutrons, and therefore, you are filling it in this fashion 2 plus 2 plus 2. So, what are the energies? This is delta, this is delta, this is delta and so on. So, you have for these 2 you have E2, calculate E2. For this you have 2 particles at delta. So, 2 times delta, then you have 2 particles at 2 delta, right. These 2 particles are at delta energy, then these 2 particles are at 2 delta energy and these 2 particles are at 3 delta energy and so on. So, this is 2 particles at 2 delta energy, then 2 particles at 3 delta energy, and how many terms are there? New terms, right. You have 2 new particles to be distributed. So, new such terms will be there. So, 2 delta taken common, 1 plus 2 plus 3 new terms, and that is 2 delta times nu plus 1 by 2, which is delta times nu square plus nu. So, what is the difference? How much is the difference? Obviously, this is larger than this, correct? You are filling up higher states. So, this is larger. So, E2 minus E1. What is E2 minus E1? E2 minus E1 is equal to delta nu square plus nu minus delta nu square by 2 plus nu, and that is delta nu square by 2. So, if there is an asymmetry in neutron number and proton number, if they are not equal, then compared with equal division A by 2, compared from there, the energy of the nucleus will increase by this term. Okay? If the same A nucleon were divided equally between proton and neutron, then what would have been the energy? from there the actual energy of the nucleus when you have n greater than z will be higher by this much amount. Again this is an estimate, these energy levels are not all equispaced and all those details are there, but roughly speaking this is the energy by which the nuclear energy nucleus mass energy has gone up, and if the nucleus mass energy has gone up, that means the binding energy is decreased. Okay? Binding energy is remember the total rest mass energy of protons plus total mass energy of neutrons minus the binding energy, that is the nuclear energy. So, if this nuclear energy is increasing, that means the binding is going down, right. So, you should have a term in the binding energy expression in which this energy is also taken into account if n is not equal to z. So, in terms of n and z I can write this nu from here, n is equal to a by 2 plus nu and z is equal to a by 2 minus nu. So, you can subtract n minus z is equal to 2 nu. So, nu is n minus z by 2. Okay. So, this energy is proportional to n minus z square delta n minus z square and divided by 8. So, it is proportional to n minus z square. Okay. So, the term to be added here in the binding energy expression, because of this asymmetry between neutron number and proton number, will be minus or plus some constant that I write a s y m. S I have already used here for surface, so I cannot take one letter. So, that is why I am writing s y m symmetric. This coming from the symmetry or rather asymmetry. So, this times n minus z square, and then what is the delta? This delta is there. So, what is the estimate of delta? Okay. So, if there is some energy and there are a nucleons and you assume that they are equally divided, it will be as 1 by capital A, right. So, this divided by capital A. This is the energy term to be added here. So, now what is the situation? Apart from volume, from where this is coming because in the nuclear volume you have all those nucleons which are interacting with each other, nuclear attractive force creating this binding energy. This is positive. But then from this you have to subtract this surface part, because the nucleons at the surface they do not find those many neighbors, they find less number of neighbors. So, the contribution from here is negative. So, from this I am subtracting this, then this is Coulomb repulsion and this is coming from Pauli exclusion principle, this is coming from discrete energy levels for the nucleon inside the nucleus and all those things. So, this is that asymmetry energy. Apart from that, one more term is important, and that is to be concerned with pairing. Pairing of neutrons and pairing of protons. What is that pairing business? Once again, quantum mechanically the particles have the nucleons have their own wave functions, and when they combine, when they couple, then two protons with opposite angular momenta, if they combine to 0 total angular momentum, we say that they are paired. Okay. So, if you have two protons and this has got some angular momentum and this has got another angular momentum, and if these combine to give you a total angular momentum of 0, right, then we say that they are paired. and it so happens if that is the case, then the energy goes down. Energy of this kind of coupling will be lower than any other kind of coupling. If these couple in a different fashion and give a non-zero angular momentum, then the energy will be higher, and if it gives zero angular momentum, then it gives lower energy. So, pairing lowers the energy. Okay, this is called pairing. So, protons and neutrons, they would like to make pairs of this kind, right, this kind. So, pairing lowers the energy. Experimentally, it can be seen in what we called neutron separation energy. What is neutron separation or proton separation energy? And this is something like ionization energy of your atoms. So, if you have a nucleus having certain protons and certain neutrons, and you want to take one neutron out, okay, this is a bound system, everything is bound, you want to take one neutron out, how much energy you have to supply? That is known as neutron separation energy. Similarly, if you have a nucleus and you want to take one proton out, how much energy you have to supply so that one proton can come out? That is known as proton separation energy. So, if you take the data for this neutron separation energy, and if you look at that, you will find that for even n, this neutron separation energy we write it as n, and proton separation energy as p. So, if n is even, then Sn is large, and if n is odd, then Sn is low. This is one step ahead. Go for n equal to 86, then n equal to 87, then n equal to 88, n equal to 89, n equal to 90, and you see the fluctuations. The separation energy is large when it is even, and then the separation energy drops when it is odd. Just add one more neutron, 87, let us say 86 to 87, it will drop, 87 to 88, it will again go up. So, this neutron separation energy oscillates and is large if n is even and is lower when n is odd. What does that mean? If n is even, all those neutrons are already paired up. They prefer pairing because that lowers the energy of the nucleus. So, once it is paired, it is difficult to break it. You have to supply more energy because the energy had gone down. So, you have to supply that energy also to break the pair and then take the neutron out. Whereas, if this capital N is odd, then surely there is one neutron which is not paired to anyone, right. If this capital N is odd, not divisible by 2, then not all neutrons can form pairs. Okay. So, this final neutron, this last neutron which is unpaired, it will consume less energy to go out of the nucleus, whereas if it is n is even and all the neutrons are already paired up, then it will be difficult to take a neutron out because you have to first break the pair. For breaking the pair, certain energy is needed, and then you have to take one neutron out, right. So, that pairing lowers the energy. Another evidence for that is number of beta stable nuclei. Number of beta stable. What does this mean, beta stable? Number of beta stable nuclei, the nuclei which are stable against beta decay, beta plus decay or beta minus decay. So, you remember that figure n versus z once again. So, in that middle part you have all stable nuclei, and if you are on one side of it, it is proton rich, and proton converts to neutron by beta plus decay. On the other side of that stability region, you have neutron rich nuclei, and there a neutron converts into proton through this beta minus decay. So, beta stable means those stable nuclei which do not decay by this beta process, neither plus nor minus. So, if you look at those numbers, the number of even nuclei, what does this mean? Z is even and n is even, they are called even nuclei. So, in that number it is somewhere around 165. Okay. And odd A, one of the two is odd, that number is around 105. So, either Z is odd, n is even, or Z is even, n is odd. So, that is known as odd A nucleus. This is even nucleus, this is odd A nucleus. A is odd. A is odd means one of them is even and one of them is odd. So, if you search for all such nuclei which are stable against beta decay and for whom one of the two is even and the other odd, that number will be around 105, one this side, that side. And then if you look for odd nuclei, if you look for this odd nuclei, that means Z is odd and n is also odd, the total number is even. Okay, total number is even. Here also even nuclei also total number capital A will be even, but here separately both are even, here separately both are odd. This total number is only 4. And since there are 4, I can remember that, and these are the lightest 4, I can just name them. One is what you called deuteron, right, heavy hydrogen, nucleus of heavy hydrogen which contains one proton and one neutron. So, ordinary hydrogen just contains one proton, but then you also have heavy hydrogen where the nucleus contains one proton and one neutron, and this is called deuteron. This nucleus is called deuteron. It is stable, it does not decay. If it is there, it is there. Total abundance is small in total number of ordinary hydrogen is much more than this heavy hydrogen, but whatever is there, it is stable, it does not decay. Next will be Z equal to 3, lithium, 3 protons, 3 neutrons, lithium 6, stable. 10 boron, 5 proton and 5 neutron, and what is 4th? Next in the series, Z is equal to 1, Z equal to 3, Z equal to 5, Z equal to what element is this? Nitrogen, 14 nitrogen, 7. These are the only 4 odd nuclei. So, that means somewhere this nuclear force prefers even things. The number of stable nuclei with even configuration is much larger than odd configuration. So, odd is really odd. If you have one odd proton sitting here, one odd neutron sitting here, then there is a great chance that either this neutron will convert itself into proton and pair up, or the proton will convert into neutron and pair up, depending on the other things. Pairing itself would prefer that we have 2 protons or 2 neutrons than 1 proton sitting here and 1 neutron sitting there. Okay. So, that means pairing lowers the energy, and if it lowers the energy of the nucleus, that means it is increasing the binding energy. So, for even it should increase the binding energy, for odd it should decrease the binding energy. We can take a reference at this odd A nucleus, we can take the reference point here, and we can say that if it is even binding energy is increased, if it is odd then it is negative, decreased. So, we add another term here which is delta. We write it delta, it happens to be, it also depends on capital A. So, this delta, which is known as pairing energy, term. This you write as delta equal to 0 for odd A nucleus, and you write as plus AP A 3/4. Which one? Binding energy positive, going up, even or odd? Even. Okay. For even nuclei, the whole energy is going down, pairing lowers the energy, and energy of the nucleus going down means binding energy is going up. So, plus and then minus AP by A 3/4 for odd nuclei. So, that finishes the job. Now, these constants, what is AB, what is AS, what is AC, what is this A asymmetric, and what is this AP? These constants are to be determined from the measured masses of these nuclei. Okay. Atomic masses are very well measured, proton mass is known, or hydrogen atom mass is known, neutron mass is known. So, from these measurements one can find those binding energies. These are the experimentally available data, and then you adjust these constants so that experimentally measured binding energies can be reproduced. So, that is how you fix up the values of AB, AS, AC, ASIM and this AP. This you can see from the textbook. Okay. What are those values of these constants which give you a nice fitting of all the experimental data. Okay. Now, I will show you a slide where relative importance of these terms will be shown. So, look at the graph. So, you have this graph on the screen. Y axis side here, it is binding energy per nucleon, and this side is A, capital A, and this line here, top line that you are seeing, this is your volume term, the first term. Just take the volume term. The first term is just AV into A, binding energy is AV into A. If you look at your expression of binding energy and you calculate binding energy by A taking only the first term, it is just AV, constant. So, that is this constant line. Then this, when you add the second term, that is the surface term. Okay. So, A is increasing on the x axis. So, you subtract from this AV this term As into A to the power 1 by 3. Remember, it is binding energy divided by A, that is plotted here, and you have written the expression of binding energy. So, from binding energy of A, when you take first and second term together, then you get this term, this curve here. So, this is the surface energy contribution that has been subtracted. This is the surface energy term contribution that you have subtracted from that volume term to get a final curve like this. So, this curve corresponds to both volume and surface term. Then the third one that you are seeing here, this is when you also add the Coulomb energy, the third term in the expression, that Coulomb term, the third term in the expression, that Coulomb term, that is also subtracting from the total binding energy. So, this much is subtracted, this is the Coulomb contribution. So, this much is further subtracted, third term, then you get this one. So, see the relative contribution, this graph I am showing to give you an idea of how much is the surface contributing, how much is the Coulomb repulsion contributing. So, at this particular A, this A will be somewhere around 180 or so, this point. Okay. So, this is the volume energy, this whole thing is volume energy, it is coming from that volume term. Then this much is surface term which is subtracted to get this, then this much is Coulomb, to subtract it you get this, and then from symmetry you have a smaller contribution, and then you get this, and of course pairing is not shown here. Okay.
So, you have seen the relative contributions coming from different terms, the volume term, the surface term, the Coulomb term, asymmetry term, etc. And that pairing I have not shown, but one can calculate, it is close to that asymmetry term. It depends on capital A, how much is capital A. And once I have this formula, and once I have the values of these constants AV, AS, AC, ASIM and AP, I get a tool to calculate mass of any given Zn combination nucleus. And therefore, many of the trends that we see in nuclei for a particular capital A, how many protons should be there, how many neutrons should be there. You know that for light nuclei, proton neutrons are roughly equal, number of protons, number of neutrons are roughly equal. But for heavier nuclei, the neutron number is much larger than the proton number. Similarly, there are many other trends. So, all these trends of where the nuclear mass is involved or the rest mass energy of the nucleus is involved. So, now we have a tool to calculate such masses, calculate such rest mass energies, and then see whether those trends we can understand using this or not. So, in next lecture I will be using this. First I will give you the values of those constants which are obtained from fitting the known masses of nuclei with this formula, taking these constants as adjustable constants. So, we adjust the values of this constant so that the masses, the known masses, experimentally observed masses can be best reproduced using the semi empirical mass formula. And I will give those values which are obtained from this, and then using this we will look for some of the general trends of nuclei. Okay? That is for today.